Hi guys. Yesterday we've seen CNN, convolutional neural networks. We looked at concepts as convolution, padding, strides, and that's with convolution layer. Then there is pooling layer. Pooling layer has two concepts. One is max pooling, another one is average pooling. And the majority of the gaps that we have seen is how do we pick up the we have filters or kernels, and these filters or kernels have the numbers like you remember 111 0 0 0 -1 -1. For vertical lines, horizontal lines, he has explained something. uh, so if we call them as w1 w2 w3 w4 w5 w6 w7 w8 w9, so these are all weights, like parameters, and then these parameters we need to see how we derive those two things, how we initially pick a parameter, and then we need to look at how we uh, optimize these parameters in a way that the kernel performs in a proper way, and then it aligns with whatever output that we are requiring. So these weights are similar to the weights that we use in a neuron. Only thing is we are not calling out that it is a neuron here. Uh, Okay, let's. So, what do you use for calculating weights or optimizing weights in a neural network is most probably the backpropagation. Um, so, backpropagation mm, can be used in order to derive the weights as per need. So, if we look at how the backpropagation, how the backpropagation will work in in a artificial neural network. For So derivative calculation like W is equal to W minus learning rate into derivative of loss to respect to W, right? That's what we calculate. So here also same formula will apply, but the challenge is because it's not in the convolution layer is not in format of not in a format of a normal neuron. We would like to look at um, we would like to look at how the derivation would happen. That's the only thing. But if you look into it, I should put it on a paper somewhere. Let me think through it. So, how convolution and neural networks could be linked? What happens in a neural network is you give. Let's assume that all the pixels are features x1, x2, xx, or so on. N by n means xn and x xn square. Okay, xn square will be our last one, like because x1, x2, x3 if you go. So, or let's say n pixels, like the count of the pixels is n pixels. So if you have x1 to xn, if you give it to neuron, what will happen? Input layer, um, each of the input layers will take all n of them, and then they'll multiply. But what we are doing is we are, instead of giving all n to this thing, we are going in a different route. So x1, x2, x3, x4, x5, x6, x9, x10, x11, x12. And we are taking a, doesn't matter, whatever. So we're taking 12 features, and means 12 pixels, 3 into 4 image. And now if we apply a filter which is 2 by 2 on this, then it will convert into, no, it will convert into 1 2 3 4 5 6. It will convert into 2 by 3 matrix as in Z1, Z2, Z3, Z4, Z5, Z6. And filter, let's say kernel one, let's call it as K1, K2, K3, K4 if you put it on it. Then what you're doing is, so in a in an neuron, we are passing all the features. Instead of it, we are distributing the features and we are passing it to multiple neurons. That's how we should look at it. But how do you distribute is basing on the kernels, right? So that distribution itself, I think that's where the it's let's write it in a straight line and say x3, x4, x5, x6, x7, x8, x9, 10, 11, 12. We don't need all that, but first neuron will take x1, x2, x3, x1, x2, not x3, x1, x2, and then x4, x5. That means here x4, x5. This is first neuron. Second neuron will take x2, x3, x2, x3, and x5, x6. 1, 2, and then it will take x4, x5, x7, x8. X7, x8. That is third one, third neuron. And then fourth neuron will be x5, x6. X5, x6, x8, x9. Fourth. Fifth will be x7, x8. And x10, x11. Fifth, x8, x9. Sixth, and x11, x12. This will be sixth. So this is how it will pick up the features, 12 features that are there. It'll distribute it across 6 neurons. If if you have 2 by 2 weights in kernel, K1, K2, K3, K4, these weights will be reused across 6 neurons. And matter of fact, they will be repeated. The weights will be same for all 6 neurons. One good thing, which is not good, but anyways, there is a after convolution and pooling, there is also a feed forward network, which is ANN. So that's fine there because there the weights will vary, so which is okay. But here we are for the image, it's more scaling down is the objective, so makes sense. Scaling down or feature extraction. So convolution is feature extraction. Uh, Pooling is scaling down, and then an ANN. So the features are being distributed into the first layer. That is what is being done in convolution. Convolution and pooling together, if you look at it, it's can be done in one neuron. It's convolution is equivalent to the linear regression equation that we do in neuron, and then uh, activation function on top of it is similar to pooling. That is activation function in this scenario either is max of or average of. These are the two functions that could be used in the convolutional. So in short, the uh, convolutional network concept of convolution and pooling is also and layer within the neural network. Only difference is usually in a neuron that what we do is we go for a linear regression plus an activation function on top of it. Instead, what we are doing here is we are doing a and then in normal neural network layer, hidden layer, we give all the input features to each of these neurons. Instead, we are not, because the size of the input is very big. We are splitting the um, one second. We are splitting it. We are splitting it, but if you look at the sum of this, see, we get Z1, Z2, Z3, Z4, Z5, Z6. If you look at the sum of them, again we get K1 X1 plus K2. I mean K1 X1 plus K2 X2, or K1 plus K2 into X2 plus K2, K3, X3, K4, X4, like that. We would get the same number. Some multiples of those features are coming because if we do a sum of it, so it's like altogether giving it into one particular it itself mathematically. But picking up a proper kernel will help in extracting features is their concept. Okay. But again, I forgot. See, I said we are talking about one kernel, but the convolutional neural networks is not going to work on one kernel. It's gonna have multiple kernels because one kernel will extract you one specific features. So if you have multiple kernels, then this process that I'm speaking on will actually get repeated. That means okay, if they are repeated, are we, yeah, all of them that are repeated, we are putting them into putting them into single the data set and giving it as input to ANN. Correct. So if you have three filters, all of 2 and 2 by 2 size on a 3 by 4 matrix, then each of them will give you 2 by 3. That means 6 outputs. And if you have three filters, it is 3 into 6, 18 outputs. Then the 18 outputs are individually considered as x1 to feature 1 to 18 feature 18, and all 18 features are given as input to the neural network KNN. Then if you consider one filter is 6 neurons, so instead of making it 12 neurons, you are making it 6 neurons. And then these 6 neurons, if they are actually, if you're using multiple um, filters, it will be repeated. So it's actually more than, it's close to, if you have more filters, actually it is more than giving all the pixels individually to a neural network. I think is the calculation is little easier because we are considering we're distributing the features, 4 features at a time, or we're breaking down into pieces and then doing a one filter at a time. Yeah, yeah. I think it's the convolution overall part is uh, is to optimize it mathematically. Now, in today's world, if you have enough compute and enough memory to handle large images, I think if you can give without convolution, if you give it to NN also, it would work in the same way. This is some statement I should validate it somewhere. Only thing is convolution introduced. Uh, so ANN can do training on image, and CNN can do training on image. But why CNNs are being used is to optimize the calculation or optimize the overall compute and memory requirements of a neural network. That's the way I understand. So we need to see if we don't do, especially convolution is nothing but using different kernels to extract different features, which is what exactly the ANNs also do. They adopt to the input data and extract features, understand the patterns, and extract features. So if they are also able to do the same thing, if what is the performance of an ANN compared to performance of a CNN, we need to see. I think CNN is more an optimization of ANN from the compute and memory perspective. That's my understanding. But let's have this as an open question. Let's discuss with somebody else to see this difference. Okay. Now we'll get to the back propagation. That's the one that's pending. I'm watching this video. This guy has taken I'll just quickly ping you on page. So this guy has taken a 5 by 5 matrix image, 5 by 5 pixels image, and then he's used a 3 by 3 kernel or filter, and he's calculating the Z outputs. So he got, and he's using stride 2. So A1, A2, A6, A7, sorry, A1 to A13, and then A3, A3 to A15, A11 to A23, A13 to A25. These are four sets that are passed to this kernel, and the kernel gives output as Z1, Z2, Z3, Z4. Okay, that's the math. And then he says, instead of using ANN, to simplify the explanation and stuff, he removed the bias term in Z, or let's say imagine even if it is that doesn't matter. And then he's directly calculating it with one output layer with one neuron. Let's say some logistic function or sigmoid function or softmax function or whatever. We use that, and then we take this input and give predict an output, right? It is possible. Okay, ANN can also have one single neuron, and we can still call it as ANN. So, um, what happens here? Actually, it's good, but thing is, yeah, so X is not there. This guy is a bit. Oh no, there is no derivative of X. It's just multiple. So this is cool. So we get back propagation. Back propagation is clear. We need not follow this guy with respect to. So what he explains is all back propagation one, two, and stuff. So back propagation we understood, but thing is, yeah, then CNN is done. But let's look at his program also. Mhm. వీటిది 2 years ago చేసిండు. 27 November 2021. Okay, so that is cool. Um, Things CNN we are good. We can move to RNN. Yeah, we'll complete RNN. We are skipping the coding piece part of it. We're supposed to spend some time on coding. At least alternate days, I thought I'll pick up Jane in parallel, but I'm still stuck here. So, okay, once RNN is done, then it'll be coding and generative AI and NLP. So these three things should go in parallel. We should implement code for all the models that we have learned till now. So we learned linear regression, logistic regression, naive Bayes, decision trees, um, k-mean clustering. Um, mm, I mean, that's not a model, but we've also learned about principal component analysis. What else did we learn? Something we have learned we can't understand. I mean, decision trees and random forests are together. Boosting is also together with decision trees and random forest itself. Um, that's it. Neural networks, CNN, RNN. Anything else that we have learned? I don't think so. I think we could. That's all. That's all we have learned. We good. So with that, we'll implement all these in code and see how they would work and how the code in TensorFlow or Java libraries that are there? How does it work? And stuff. Quick question I want to ask ChatGPT is, where is ChatGPT now? Yeah, here. I know it will be expired because I was not using it. Login. Email. Login here. Like a list of libraries can use for building neural networks and a brief comparison between them. Okay, TensorFlow, PyTorch, Keras, Cafe, MXNet, Chainer, CNTK. Okay, so let's say this is our libraries alpha building networks and deploying models and Python. That's what it TensorFlow. Offers high-level APIs like Keras. It's flexibility and scalability for building complex neural networks. Mhm. And then PyTorch developed by his fair offers dynamic computation graphs, making it debugging provides a Pythonic interface. This is more flexible than static graph approach. Gaining, gaining popularity in both academic and industry due to its ease of usability. Keras has a network API that runs on top of TensorFlow. The tool designed for fast experimentation with API networks was useful. Kept around by Berkeley Vision and image processing tasks on networks. Applications. Thanks. Mhm. That was flexible and intuitive approach in your network process. Applications CNTK. And create a table rating them from 1 to 10, where 10 is the best, comparing on performance, time, compute and memory utilization, and let's try this. See, let's see ChatGPT if it will work with this. It's giving rating also. Performance, time efficiency, compute utilization, memory utilization. The overall performance of the library in terms of model training speed, inference speed and scalability. Okay, that's nice. Time efficiency, how efficiently the library utilizes time during training. Compute utilization, memory utilization. Okay, let's see. TensorFlow is 9. Every test all is 8 sevens. Time efficiency, PyTorch and Keras are 9 and rest all are 7, 8. Compute utilization, TensorFlow is 9 and rest all are 7, 8. For memory utilization, Cafe is the best as it seems, 9. Rest all are 7, 8. Okay, that's a good thing to learn, right? Nice. Okay, I think we good. We can move on tomorrow to RNN. Stop, join work, yes. Go here. Bye, guys. And stay.